Okay, but now we're ready for section 3.2, and that is called strong operator convergence. Okay, and let's not scroll back and forth again. Let's just draw this diagram quickly here. Okay, so remember the aim is to have a convergence that is weak enough so that the limit of a sequence of finite rank operators can be across that green boundary on the other side where the invertible operators are. Okay, and if you want convergence across this boundary, you need something that is weaker than uniform convergence. Okay, why we will still call that new convergence strong convergence is a different story. It's going to be weaker than uniform convergence, but it's going to be stronger than some other convergence that is already called weak convergence. Okay, now let's play around and see what we have to do. Playing around means let's look at the very simple invertible operator A and try to approximate that by finite rank operators, and then you will see what kind of approximation that would be. And when we say very simple invertible operator, we usually try the identity. And for the identity, you obviously need x to be equal to y. And because we want to play around explicitly here, we should pick something more concrete. Let's take L2, our sequence space with square summable entries. So let's write down what our operator A is doing. So acting on the sequence space L2, it should take a sequence of real or complex numbers. So please do not confuse these x1, x2s with the solutions of our simpler equations that we've been looking at before, because they are elements of x, and these little x's are elements of real or complex numbers. Okay, and because A is the identity, it's just taking this infinite vector here to itself. Okay, and now you want to approximate this action by an operator an that is finite rank. So again, an would take the whole sequence and then produce something finite dimensional. So why not truncate our sequence after just finitely many entries? So we have x1, x2, and so on up until, let's say, xn, where this n is just the number of that an. Okay, and then the rest is just replaced by zeros. So this operator is taking your infinitely long vector and just truncating it after n entries, replacing the empty slots by zeros. Okay, well, if you do that, then your operator can only produce finitely many data over here, so it's gonna have a finite dimensional image and therefore a finite rank. So yes, this is finite rank, and yes, this is invertible. And now all we have to understand is in what sense does that sequence an approximate our invertible operator A. Well, it should be clear that this cannot be uniform convergence, but I mean, let's check it anyway. So for uniform convergence, we have to look at the norm of A minus an and see whether or not that goes to 0. Well, by definition, this operator norm is just a supremum of all the norms of images of A minus an over little x's that have norm 1. And because we are in L2, well, we are evaluating the x norm, the norm of x, as well as the norm of ax and a minus anx and the 2 norm. So clearly, this expression is just ax minus anx, and that means we have to take this green vector here minus that red vector here and evaluate the 2 norm of this. Okay, but it's easy to compute this difference. The first n components cancel, and then you get the other components of x. Good. So for the computation of this supremum here, you just have to ask yourself, how large can this norm become if that norm is limited to 1? Okay, and then of course, because this vector here is essentially part of that vector, only with the first n components deleted and replaced by 0, the answer cannot be more than 1. But maybe can it be equal to 1? And the answer is yes. Just take the infinite vector x that has a 1 at this n plus first position and everything else equal to 0. Then that expression here would give you 1, but of course at the same time that expression would give you 1. Okay, but that little discussion here shows that the supremum must be equal to 1, obviously independent of the value n, which means that it does not go to 0 as n goes to infinity. So we can answer no here as predicted. The key observation here is that this element x depends on n. So if you make n a bit bigger, then this vector is just not helping anymore, because then the 1 is within the first n entries and hence gets truncated. Okay, let's try to learn from that example. So again, uniform convergence means the norm of a minus an goes to 0 as n goes to infinity. And of course you can abbreviate that as follows. You could say that the limit equals 0, or we just plug in the definition of the operator norm. So this operator norm here is just replaced by this supremum. And as in the previous example, we have already rewritten this difference of operators applied to x as a difference of one operator applied to x minus the other operator applied to x. For the unlikely case that this is helping much, you can also spell this out very explicitly. Right, so the fact that this supremum here is small is written down here. You're just saying no matter what x you try, it's small, less than epsilon. Okay, and the fact that this is going to 0 as n goes to infinity is written here. So your n0 is telling you how large n has to be in order to make this expression smaller than epsilon for all x's. And in our example, such a universal n0 doesn't exist. It will always depend on the x for which you want to make this smaller. So we could make this statement a lot weaker by moving this bit before the choice of n0. Then it would say every x can have or may have its own n0. Okay, let's spell it out what that means then. Then you arrive at this. But now this expression here can be abbreviated as just this convergence to 0 here. Okay, but that statement here is robust under scaling of your little x, so you can just take this condition away here, that the norm of x be equal to 1. Or instead of saying this norm here goes to 0, you could also say this sequence in y converges to that element of y, in the norm of y. But that is what you usually call pointwise convergence, because for every point of x, you have convergence of the images as n goes to infinity. Maybe it helps if we abbreviate this line here by the following, because basically we're saying that the limit of this expression is 0 for every x. So you could say the supremum of all x's of that limit is 0. And this is somehow telling us that on our way from uniform convergence down to pointwise convergence, all that is happening is this limit and that supremum changing places. Okay, and if you think about it long enough, then you will recognize the mechanism that we observed first in this example here. Okay, now I think we're really ready for the definition. An operator sequence AN converges pointwise, and in fact often people say strongly instead of pointwise, to an operator A if for every point x and x, ANX converges to AX as convergence in the space Y and as n goes to infinity. And if you want, you can spell this out like this, of course. As a notation for strong convergence, we will use the convergence with just one simple arrow as opposed to the two arrows from uniform convergence, which is stronger than the strong convergence. Okay, and then just as a side remark, why do we call it strong convergence if it's weaker than uniform convergence? Well, because there is another even weaker convergence, and that's what's called weaker convergence usually. And there you expect even less than that. You expect that for all functionals, for all elements of the dual space of Y, functional applied to this converges to the functional applied to that as n goes to infinity. And like I said, this is called weak convergence. And in case you're asking with how many arrows that is abbreviated, if it goes down from 2 to 1, how much further can you go down? The notation is just the upper half of an arrow. Okay, but that was just a side remark. We are not going to be looking at weak convergence here.